Hello. So today we'll be looking at how to do formal proofs for algorithms. So what does a formal proof of algorithm mean? So, so a formal proof of an algorithm has two parts. Firstly, it has a part where you try to prove the correctness of the algorithm. In other words, you try to prove that the algorithm outputs as it is expected to output. And the second part is when you prove the runtime computation, so that you can prove that the number of steps or other complexity measures of the algorithm is as claimed. So we will be showing how to uh, use or how to prove these two parts for the binary search algorithm. So this will be an example we will be using. So you guys remember the binary search algorithm from last time? So here is it. So binary search is the algorithm that takes an input, an array A of length n and a number b, and checks if there exists an I such that ai equals to, sorry, this should not be n, this should be b, right? So whether the b is present in a in the present in the array or not, and if such an if such a I exists, then it should output the index of the array where it is present, right? So this is what a binary search algorithm is supposed to do. Now let's just go to the pseudocode of the binary search algorithm. So here is the pseudocode. Let's quickly go over the pseudocode once. What does it do? It tries to initialize something, then it has a long big while loop, and the inside the while loop it does some set of commands, right? So if we want to say a little bit more about what it does, maybe this will help. So it takes this array A, so say here is the array A, and it first initializes the L to the first index and U to the last index. Now it goes into the while loop. So in the while loop, what does it do? Okay, the while loop basically continues till the time no output is produced. So as soon as an output is produced, the while loop stops, and note that as soon as the while loop stops, the algorithm also stops, right? So here what it does, once it goes into the while loop, it checks is u less than L. So note that to start with, u is not less than L, u is much bigger than L, right? So if u is less than L, then the output is B is not present. So that means that is a crucial place. So in some sense, if u becomes less than, so if this u becomes less than L at any point of time, the algorithm will just stop. Now say u is not less than L, then what it does, then it looks at the first variable, okay, then it sets a m, which is basically, if you see this one, it is actually u plus L by 2, so somewhere in the middle. So this is something like u plus L by 2. And it looks at this particular index. So if it finds that B is sitting here, then it outputs that position M. Okay, this is a kind of very easy thing, right? If actually you find a particular position where B is present, it outputs that position and the game over. if AM is bigger than M, AM is bigger than B, then it does something else. Okay, what does it do? Now we have to go understand that okay, what is going on here. That A is the array that is sorted in an increasing order, which means these functions, the ordering goes from left to right, right? It goes up along the arrow. So which means that if AM is more than B, what does it mean? This element is bigger than B. So if this big element is bigger than B, then if at all B has to be present, B must be on the left side of AM, not on the right side, right? So what it does is that in this case it reassigns U. Okay, maybe I can use some slightly more fancier gadgets. It reassigns U to the place which is just M minus 1, right? This is equals to M minus 1. Okay, so this is what it does. We of course know that B, if B is less than AM, it must be within this set of cells. It cannot be here because if it was here, the algorithm would have stopped before. But so that means it must be between this 1 and M minus 1. So this is the main idea. Now, if that is not the case, if AM is bigger, then what happens? Let's see. Then U is here, right? Oh, sorry, made a mistake. All this beautiful stuff doesn't work, turns out. Sorry. Let me just draw this. So U is here, AM is here, and I don't have anything over here, right? And what we now see is that AM is less than B. What does it mean? That means this quantity in this M again is less than B. So if B has to be present, it must be on the right side of AM. And since this cannot be AM again, because if it was, then if condition, the first place would have taken place, it must be in this chunk. So in that case, what it does is that it assigns L to M plus 1, right? So this is for the M plus 1, and it continues. So in the next step, for example, what will happen? At this point, I should have this one gone. M. We would look at the next thing, which is M, which will be in the middle again, right? This will be the middle of L and M, L and U, and again it will look at this middle portion and accordingly make a decision. So this is the understanding of the binary search. But of course, this cannot be a formal proof. How do you write this proof of correctness in pen and paper, right? So to write the formal proof of correctness of an algorithm, you kind of have to do 4 steps. The first step, you have to check for the correctness of the linear part of the algorithm. So in this particular thing, the linear part of the algorithm is just the initialize, so there is nothing much to be there. But you can have algorithms which have some more other parts, where you do some operations, you fix something, and so on and so forth, right? Good. Then you look at the loops. That loop can be for loop, in this case it is the while loop, and so on. And in this loop, try to identify what is called a loop invariant. What is a loop invariant? It's the loop invariant, the property that is preserved during the loop. That will help you to kind of argue when you come out of the loop, what property do you have retained. This is very essential for formally arguing about it. So, for example, in this case, what can be the loop invariant? Right? So, the loop invariant in this case could have been something like that B is always bigger than or equal to A of L and lesser than equals to A of E. So, this is a statement. This can be a loop invariant. Now, this particular statement you can prove. So, say you start the loop, when you enter the loop it is there, right? Of course, because when you enter the loop, L equals to 1, M B equals to 1, and so B is basically here. Oh, so maybe I should write it here. Is this one? If B exists, if B is in the set, right? So, if B is in the set A, then it is in between these two. Got it. Excellent. Now, this statement is true when it enters the loop. When you are in the loop, so after the ith iteration, this is true. Then you have to argue that what happens in this set of conditions. Is this quantity, after you start here and you finish here, in these two steps, is this loop invariant still holds? And you can argue, you can see in this particular setting, this will work. Because if you remember, however, the way in which we moved that L and U is exactly so that B, if it is present, should be kind of be in the between U and L. So, both these two conditions actually did that. And now, when does it stop? It stops when you either have output whether B is not present or B is in the position M. So, in some sense, the algorithm will keep on going until the time it will stop at some point of time, and in that case it would have outputted both of them. But note that when can its output B is not present? It can output B is not present only when U becomes less than L. But while in the while loop, what we have that this loop invariant is always preserved. It means that you can output B is not present only when this loop invariant does not hold, and that can happen when B is not in. So, this is the way you argue that if the algorithm ever outputs B is not present, the function that means that B is actually not present. And when does this thing B is present? It is present when it finds a M such that AM equals to P. So, here is the interesting situation, right? We have a loop invariant that we found out, and we can ensure that whatever outputs comes out, So here say, so that means if uh, this output comes out, or if this output is output, the function value, the actual right answer will be output. Now the only other thing left for an algorithm is to prove that an algorithm stops, terminates, and this is something we have not yet. So in just I will come to that last part later, but in short, you start with checking the correctness in the case of linear part, then going over the loop invariant part and proving that the loop invariant holds. Then you have to ensure that the loop do exist at some point of time and complete the A and proving that the algorithm terminates and the final output is correct. So what we have not done so far is show that the loop does exist at some point of time and the algorithm terminates, right? So this brings us to the, so I have not used it. So here what we have is that the loop invariant for binary search is if B is in A, then B is between A, L and A. This is the loop. Okay, and only thing left that we have to show is that to show. So I have not yet proved it, but you have to prove it that this loop invariant holds, and we need to show that the loop terminates. This is very important. Whenever you have an algorithm, it is important to prove that an algorithm terminates. We have not yet shown that. It's a kind of a chicken egg problem in some sense. Which one do you prove first? Whether the algorithm terminates or whether the algorithm outputs the correct answer. So here I have given this thing. So what we have is that if the rather I would rather say that whatever rather if output is produced, the output is correct. So this is something that we have convinced ourselves, right? This is what we have convinced ourselves, and what we need to show is exactly this part. This is what we need to show, and once we do that, we are done. So there are three parts. You first prove the loop invariant, then you show that the whatever the output is correct, and the third you show that the loop terminates. And this is the fact. Okay, now showing that the loop terminates is also very similar to how to argue with the runtime of the algorithm. Now to understand the runtime of the algorithm, let me go back one step to that binary. So note this one. What is the number of steps it does? So there is only some constant number of steps here, and within a particular loop, there is only constant number of steps, only within a particular iteration. So what we need to bound is the number of times the while loop or the loop continues. So this is something that is almost always, the loops are the hardest thing to argue. And the way to argue is to using what is called a potential function. So a potential function is a function that we can say that, oh, see, this keep on going down or going up, and we kind of prove that we can use it to prove that the number of times the loop exists. So in this case, Okay, we can use the potential function as u minus l, the distance between them. And note that after every iteration, u minus l is halved. I am not proving it, I leave it to you guys to prove it, but this is a easy to check, right? And what we also know, that at the start u minus l is actually equals to n, n minus 1 or whatever. So you start with a potential function which is at n minus 1. At every iteration it is halved. So that means, so the number, this implies the number of iterations is less than or equals to log n minus 1 base 2. Thus, after log n minus 1 base 2, the potential function will go to 0. Okay, this is one thing that I have not proved. What happens when u minus l, when the potential function becomes 1 or 0, when u is equals to l, what happens? Okay, so this is one other thing to check. Okay, to check what happens when u equals to l. Proves that when u equals to l, this is a special case, and in that special case the function will terminate in one more extra iteration. Okay, so either you will, so in this many number of steps, in log n minus 1 base 2 number of steps, you will ensure that u becomes equals to l, and in that case you can prove that once you are here, the number of steps that for which the algorithm can go further is only 2 iterations. So using this argument, you can prove that the runtime of the binary search is order log n, and this also proves that the binary search does stop after a finite number of steps. So this is one way of proving the formal correctness and time complexity of algorithm. Two crucial things that we have seen today is loop invariant and potential function. Now these two quantities will possibly come up again and again in the next few lectures. So I will ask you guys to kind of formally prove the binary search problem, the correctness of binary search algorithm for yourself in the gory details, so that you are comfortable with how to write the proof of a algorithm like binary search. Here I should note that there are of course lot more complicated algorithms, and this is just one of the ways of approaching a proof and the possibly the simplest way of approaching a proof. But for now this is the start. Simple algorithms can be proved, the correctness of them and the runtime of them can be proved using this technique.